Okay, welcome to class 5, where we're going to finish up with chapter 3, and this is video 1, and we have pressure and fluid statics. So we're going to talk about really two main topics in today's class. Buoyancy and stability is one of the topics, and then fluid and rigid body motion. So I think I will try to get through the entirety of the buoyancy and stability in this video. Let's see how that goes. All right, so here's our first image to think about, a cartoon. I drew this recently. And the big takeaways here is we have this pressure distribution on the outside of this floating ship that I've drawn. And what we find is that we have the center of buoyancy is because of that pressure distribution. And we also have the center of gravity. So we'll see what that means here in a bit. And here is a picture I made just to sort of describe what stability is, that kind of idea of stability. And the basic premise is a small amount of displacement, just pushing wetted over just a little bit, will cause a large reaction. So an unstable thing, when something is unstable, a small input creates a large output. And then here's an old video where I'm showing rigid body motion and the effect of it. And we can see that it creates a free surface that's affected by the acceleration in the horizontal direction. And we'll see why that is. All right, so big question is, why do things float? And more specifically, why do ships stay upright? Well, it really comes back to Archimedes' principle here. And I'm going to switch over to my camera and generate a couple notes. So, well, what is Archimedes' principle? Well, I'm kind of really butchered the story, but Archimedes was a Greek mathematician, and I believe there was a king that wanted to know whether his crown, the crown was actually made out of gold. So Archimedes came up with a way to judge whether the volume of the displaced water because of the crown was sufficient to show that it was indeed solid gold. I mean, I think the story is something along those lines. I'm really just butchering it, but that's fine. But I would say that if we're going to write something down for Archimedes' principle, we would say that the weight of a semi-submerged, I'm going to stick with the semi-submerged, and we'll see a little graph here, submerged floating object. That's why it's semi-submerged, because it's floating object, is equal to the displaced liquid, liquid weight. I didn't spell liquid. I spelled liquid with I'm really just ruining that. There you go. Liquid weight. And therefore, the liquid, the specific weight. I should just write in cursive. I think mixing cursive and small print makes me up. Times the displaced volume. And it's just like that word says, the displaced volume, right? So when you put something in the water, it makes the water rise, right? Because but it's taken up some space. And so that space, that right there, whatever that space weighed, like that chunk of, it could be any liquid, a lot of times it'd be water, but if you put something in water and it moves water out of the way, so the volume that gets displaced right there, that's going to be equal to the weight of the thing. And so I might go like the weight of the object is equal to the weight of the displaced liquid, or dispel, and then go LIQ for liquid, which is also equal to the specific gravity of the liquid times the volume displaced, right? And we can also, but interestingly enough, we could also do this as, okay, so the simple way, let me say, we could call this thing a buoyancy force. And drawn on here, there's like a little free body diagram. We see there's a force acting upward. And on this particular thing, we have this is like a lead weight. And now this is completely submerged. And this is true too. I just wrote it right up above for the floating object, but it could be also an object that doesn't float, can just have now, it can just quote unquote weigh less, right? So in this case, it's a lead weight, and so it's not going to float. We have the tension here of maybe a string at the top and a tension here at the string at the bottom. So they call that TA and TB. And if we did a free body diagram of this and said the sum of the forces in the y direction, and I said make y positive, but later on they decided z is positive. I don't know why. But we would say that we'd have TA plus the buoyancy force, because of the displaced thing going on here, minus W, and then minus this TB right there, right? So we're balancing out those forces, and we're seeing that this is what's due to the weight, due to the buoyancy force, due to this displaced. So that's an easy one, is good to go. FB is equal to gamma V right here, where this is like the big idea right there for that buoyancy force. That's the simple one. But we could also do this more complicated. So we want to kind of like understand what's actually taking place here and why this is taking place. It's because we have a pressure gradient, that pressure gradient that we've been looking at all along, that's acting along every point of this, and the pressure is always perpendicular to the surface, right? So the pressure is always pointing towards the surface right there, and in all directions, right? But it varies with depth. It's an important thing. So we could also say, as a more complicated one, that we could take the buoyancy force, and if we could integrate the pressure that's acting onto the surface, I'll just ask for surface, times the incremental little areas right here, we would also get the same buoyancy force. So it's really the cause of this is that pressure distribution acting onto the thing. Let's see, I think I have some slides with some pretty pictures, and that might enhance our learning here. So here is another, this is what the book has for the buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid displaced by the body, and it acts upward through the centroid of the displaced volume. So that's an important thing to make a statement about, right? That all of those forces are pushing toward, all those pressures are pushing towards the center, and because of this, we have a I just got the message again. I have one less than gig. What does that mean? I don't know. Is that my computer, or does that have to do with Colterra? I don't know. But anyway, they point towards the centroid of the volume. But of course, we're looking. This is a slice, so it's the centroid of the area. So here's other figures that they showed right here. You can see that if something will float when its density is less than the density of the fluid. Now, if they happen to be perfectly the same, we might have a body that would be suspended and have neutral buoyancy. But if the density of an object is greater than that of the fluid, it'll sink to the bottom. Some interesting thing of the Dead Sea has a lot more salt water, has a lot more salt in it than other bodies of water. That's the reason why it's dead. There's not a lot of living stuff inside the Dead Sea, and you could really, really, really float. Now, I've actually swam in the Red Sea, and that also has a lot more salt, and it was pretty surprising how high you will float as compared to if you go to other bodies of water. It's like it kind of went up just about to my chest, where I would float like with my shoulders out of the water, which seems really strange. Same thing's true with gases too, by the way, right? That's the difference in densities and that volume right there, sort of hot air balloon. So here's an important thing when it comes to ships and why do they float upright? And it's the same principle taking place. Let's go, get out of my way. There you go. So we have this display. Here's the displaced volume right there, and we're only seeing a cross section of it, so we see this area. But if we were to draw this carefully, I'll draw the hull carefully here, or try to, and we were to see, I'll draw over to the side that pressure distribution, right? Okay, so here's the baseline right there, and here by this is the submerged surface right here. Nothing above matters. When it comes to these forces, we know that we have a pressure distribution, that gradient that goes downwards like there. So if we kind of like look up, it gets larger and larger, then it gets smaller right here, right? So we have these little tiny forces, and they get bigger and bigger, representing how the pressure distribution gets larger towards the bottom, but they're all acting perpendicular to this. So they get like, they form like a little center right here of this. And so that right there is where the single equivalent buoyancy force acts. And what's really important about this is the idea of stability. So I think that has to be in another video, but I'll do a simple example right here for this one because I have like 5 minutes left. Okay, so here's a simple, just a demonstration of where we would use this to figure out how much the ship weighs, or how much like maybe a barge weighs, and how much like the stuff inside the barge weighs. This is actually how it gets done, right? I'm going to say that we want to answer in long tons. This is maybe new to you, but for ships, they use whatever 1 long ton, LT, is equal to 2,240 pounds. Don't ask me why it's not 2,000. It's just a traditional thing. But anyway, we want to find this thing. Let's see, it starts out with 28 feet wide, 90 feet long, and when it's unloaded, it's at a depth right here of 5 feet. And we want to find the weight, and then once they put the grain inside this thing, it goes down to 7 feet. So we want to first find the total loaded weight of the barge, right? So the unloaded weight of the barge, and then find the weight of the grain. So we'll take the volume that we got before anything happens, and so I'm just going to go little w, L, and D. And that's for the depth right there. So there's width, length, and depth. So 28 by 90 by 5 is equal to 12,600 square feet, cubic feet, excuse me. So the buoyancy force at that first state is going to be equal to the weight, which is going to be equal to the density of the water. And they say there's a river barge, so it's fresh water. That's a little key, a little thing. So we'll just say that it's going to be 62.4 times 12,600 cubic feet. And so that comes out 786,200 pounds. So it makes sense that we're going to want to divide that by our 2,240 pounds to get long tons. So if we were to say, okay, they wanted the weight, not the buoyancy force, but they're equal to each other, right? So the initial weight is going to, if we divide by that by 2,240, you get 351 long tons. And if you go look at how much a ship weighs, they'll give it to you in long tons. So now we want to find out what the grain weighs, right? Well, we're going to have the volume. We might want to go the displacement, right? The displaced volume right there, the change. So delta V is going to be once again, the width times the length, and then times the change in depth, right? So 2890, that's the area, and now we have the depth change, which is just 2 feet, right? Because it went from 5 to 7. So we get 5,040 cubic feet. And now, so the buoyancy force, I guess, for the grain, I'll go grain. It's going to be equal to the weight of the grain. And that's the specific weight times the change in volume, or 62.4. Oops, 62.4 times our 5,040, excuse me. And so that ends up being 314,500 pounds. And then once again, that doesn't do us much good because it's way big, well, it's going to be easier to compare it with smaller number. So we get 140 long tons is what that has. So we'll see that the weight of the grain is equal to 140 long tons. Simple example, but it's maybe just trying to reinforce this idea that we actually, on board ships, you'll actually see things called load lines. And because the ships don't sink the same amount in the front and the back, or the left and the right, port and starboard, we actually have a bunch of these watermarks that you'll see on these load lines. and that's how we measure how much the ship weighs. So like I could actually bring this up and I'll go ship load lines. Maybe I could have an image of this. I could save this on the ship load lines. Where you got? Ooh, what's going on here? Why is it such herky jerky? Ship load lines. These might bring up curves of the load lines. Oh man, this is not. It's going very sluggish here. There you go. So you'll see here. Here you go. Here's a picture. The center one's called the plimsoll mark, but you'll see these little depth marks, these numbers that are on the bow and the stern, and these also, here's the regulations about how deep it's allowed to go by various governing bodies. We'll have these. This is what's called the plimsoll lines right there. So anyway. This is like a little piece of information for you that maybe you wanted to know. Maybe you didn't. I don't know. But now you have it. See you in the next video.